Online people can hear me. All right, thumbs up. Thanks.
Yes. Yeah.
All right, let's get started. Any questions before we wrap up introduction and chapter 5 today? So we're going to finish block diagrams and then move on to, it's not in the textbook, but I'm going to go over like a quick math review. You'll learn this in 564, but I think you're going to learn it a few weeks too late. So I'm going to introduce you to the concepts that you'll learn in 564, but in application to controls. So we'll start on lecture 2 today as well. Any questions? Okay, so I may go to the Canvas website real quick as well. Start screen sharing. So first things first is that homeworks will be assigned on Thursdays and due the following Thursdays. And then I try to release the solutions on Saturday or Sunday. If they're not up by Saturday or Sunday, just shoot me an email. We do have a homework due next Thursday. It's fairly short. You can access it through here. Here's the grading rubric. Then you just take a look. It's going to be on block diagrams and then partial fraction expansion. And so today we're going to cover block diagrams, so you can start on that. I'm not going to cover block or partial fraction expansion live. I have recorded lectures from the past. It seems like there's like a mix of people who already know it, so I don't want to waste too much time. I'd rather get to the control stuff immediately. So if you don't know how to do partial fraction expansion, it's just two, I believe, 20-minute lectures. Yeah, or 16 and 18 minutes. There might be an error on part 1 where this is a 2K1, 2K1 plus K2 plus 3K3. It might be 4K1. I'm going to confirm that later today in this announcement. But the solution should be correct, though. Let's see. Well said. Okay, that's about it. So we get started. Put this on notes mode. Is this too dark for you guys? If lighting good? Okay. All right, so we ended yesterday going over closed loop systems, and we just started on system response. So when we look at system response, there's two types of responses. One is called the transient response, or the natural response. So this describes how a system acquires and dissipates energy. In math term, we call it the homogeneous solution. Think of the transient response as also being dependent on time. And then the steady state response, or known as the forced response, is the response of the system due to an input. In math terms, that's just the particular solution. So then when we look at the total response, we look into, it's going to be equal to the natural plus the forced response, or in this case, the transient plus the steady state response. So what does that mean in differential equations? So in differential equations, the complete solution or the total response, it's going to be equal to your homogeneous plus your particular solution. And your homogeneous is based off your initial conditions. This is based on your initial conditions. I use IC for initial conditions. And then your particular solution is based off of. Yeah, the mic just died. I will change batteries right now. All right, can you hear me? Can you hear me now?
Yes.
Okay, great. I'll just use the podium mic. So for our system to be stable, we want our natural response to be bounded or transient response. Let me swap screens again. Guess hyperlinks on my tablet isn't working. So if you look at the Tacoma Bridge. So what's happening here is some civil engineer messed up and didn't figure out the natural resonance of this bridge. And what's going on is that the energy being put into this bridge from the wind is not being dissipated fast enough. So the wind is adding more energy than it's being dissipated. So it starts this oscillation and it kind of grows unbounded until catastrophic failure. And this is an example of something that is unstable because you're not able to dissipate that energy entering the system. So eventually the bridge collapses. And I don't know if the wind was like varying in wind speed, but maybe we can assume the wind is like a constant wind speed, like a step function where it's a constant wind speed of, I don't know, 8 or 10 meters per second. And it keeps pouring this energy into this bridge. And um, this bridge has this resonance frequency. Uh, I don't know what the frequency is, but it's not able to dissipate that energy, goes unstable, and we have this catastrophe. So one thing about this video is that we'll learn more about this resonance. We'll learn more about it with Bode diagrams. We'll learn about resonance using Bode, and that's going to be Bode plots or Bode diagram. That's going to be in chapter 10. So I'm jumping the gun a little bit, but I just want to plant this into your head. So basically what happened was the failure was because Failure due to energy in greater than energy out, or energy being dissipated. If we look at dampeners in cars, the whole point of dampeners is it's trying to remove that energy from the spring, because when you have a spring, it's going to just oscillate. A perfect spring will just oscillate forever. So then dampener is there to just get rid of that energy. Uh, One thing about resonance is that even though the wind is probably blowing at a constant speed, it's able to excite that bridge at a certain frequency. And I guess the beauty of like a step function or impulse function. Have you ever heard of an impulse function? Sounds familiar. So just I guess I can demonstrate. If I hit you with a hammer, that's an impulse function. You get a lot of energy all at once, and it stops. While a step function is like if I hit you with a hammer and I keep applying that force afterwards, that's a step function. And the beauty about these two functions in particular is if I have this long rod and I hit it with this hammer, it it bounces up and down. So it has this frequency that's bouncing up and down at. And if I make this stick longer and hit it, the frequency is slower, but I hit it with the same input. So the beauty of a step function or impulse function is that you excite all frequencies, and you see which frequency is the, or like you see the system that is vibrating at that particular frequency. You don't know what frequency it's at. That's why we hit it with an impulse or step function, and that excites all the frequencies, and we see which frequencies are the resonance frequencies. So that's why, I mean, I don't think they ever, when I took this class, I never really understood the importance of impulse frequencies. But when you're trying to identify resonance, you usually excite the system with like an impulse input. And well, I'm jumping the gun by like 9 chapters, but I kind of want to talk about this now. And then when I talk about it again, it'll sound more familiar. And I guess it's kind of hard to hit a bridge with a hammer where you can see it vibrate, but with simulations now, you can kind of guess what the resonance frequency will be like. Okay, so I think that was chapter 1. And so now we can jump straight to chapter 5. We're going to change gears a little bit. This is just more things to just kind of get. You don't need to know anything about control systems. This is just more about block diagram representation and how to read block diagrams, how signals go through the block. So block diagrams are used to represent multiple subsystems. It is helpful to simplify multiple subsystems to get a workable form. So for example, feedback form, or so OL here stands for open loop form. The idea about block diagrams is that in our textbook, we usually like to get things into feedback form, and then we can apply our equations specifically for feedback form. So we can have something like here, something on the left here, be simplified to the equivalent system on the right here. So we're just going to go over some nomenclature. So here, this is our system in our signal. So these lines here represent our signals, kind of like a signal flow. And this is my system. In the textbook, I mean, they have C of S. It's just representing the domain of that signal. I wouldn't worry about it too much. We'll talk about what that means later. Sometimes you might see R of T instead, going into some, and apologies, but this might seem kind of confusing, but this is the equivalent system. This might seem a little bit more intuitive, but the R of T means that my signal is not dependent on time and not on frequency anymore. This G of S still represents that the system is represented in the frequency domain. So for consistency, it might be easier if I write G of T. One other thing in this textbook in particular is when something's in the frequency domain, they like to use uppercase, while lowercase is for time domain stuff. But if I write G of S or G of S, they're both in the frequency domain. So just use context. Um, Sometimes when block diagrams get very confusing, I just drop the T or the S because it's just too much to write. So if on your homework you don't want to write the G of S and you just want to write G, that's fine with me. Okay, so uh, the way this works is C of S, what we do is when we read our block diagrams, we multiply our signal by our system. So here our output C of S is going to be equal to our system, G of S, multiplied by R of S. Makes sense so far? Pretty straightforward, right? And down here we have our summing junction. And here what we do is we add our signals. So our output is going to be R1 plus R2 minus R3. Good so far? Uh, and then, so that's called a summing junction. Now, a pickoff point is just our signal being branched off in parallel, but they all read the same signal. So that's called a pickoff point. Uh, some textbooks, they might use a circle with an X here, or if you just use a circle only, that's okay as well. These are both the same systems. Maybe, yeah, there you go. So just use context. Sometimes they'll use an X, sometimes they'll leave the X out. Okay, a little bit more on topologies. So cascade form is when two or more subsystems are in series. In this class, we don't have to worry about, I guess, the flow of a signal. When I'm talking about that, it's like it's the order of the blocks that appear. But because we're dealing with single input, single output systems, but when we're dealing with multiple input, multiple output systems, order does matter. So the way we want to order the blocks is we want to work backwards with the flow. So like our output is going to be G2. So this is going to be number one. This is number multiplied by G1 multiplied by the input. And this is how we read the flow. And this is important only for important, or I don't say important, but necessary for MIMO system. Necessary for, when I say MIMO, it means multiple input, multiple output systems. And it might not make sense right now, but maybe just take my word for it for now. The main reason why is because with multiple input, multiple output systems, this representation is actually going to be a matrix. So the matrix multiplication order does matter. But in single input, single output systems, we're not dealing with matrices. The reason why I just want to mention this is just because I want you to build that habit now. So while it doesn't matter for this class, if you write G1 times G2 times R or R times G2 times G1, like I will not penalize you, but I want you to know that this is how you do it. And I want this habit built now. Okay. And then for cascade form, you just multiply everything in series. So G2 times G1 times R is the output. Now with parallel form, it's going to be similar to the summing junction. All we do is we look at all these signals here. It's going to be G1 of S minus G2 of S plus G3 of S multiplied by our signal, R of S. And then feedback form, this output here, and maybe I'll prove it to you as well. So this is a general equation for feedback form. It's going to be G of S divided by 1 plus or minus G of S, H of S, multiplied by our input, R of S. Do note that this here corresponds with this. So it's flipped. So it's plus or minus. If I choose a minus, which is called negative feedback, you use the plus sign. If I choose plus, which is positive feedback, I use the minus sign. So these two are related. So negative feedback, we want to use the plus sign. Positive feedback, we want to use the minus sign for this. So feedback form. So yeah, this equation lives rent-free in my head. Well, I guess if we can prove it right now, how this works. So let's look at the proof. And the way I would look at this, and this is a method that I'm pretty sure other people came up with, but I also discovered this method. I call it the signals method. I don't know what it's actually called, but basically, what I like to do is I like to look at different signals here and see what they're equivalent to. Oh, missing my plus sign right here. So if I look at this point here, the signal here is going to be H of S multiplied by the output, C of S. This signal here is going to be R of S minus plus H of S times C of S. Maybe I should choose a different color. I'll do a different color so it's less confusing. Okay, so now that we know that, let's look at the output. The output C of S is going to be equal to G of S multiplied by this thing here, because that's the input signal going into G of S. So it's going to be R of S minus plus H of S times C of S. Okay. Then let's multiply it out. C of S is equal to, and I'm going to just drop the S. So C is equal to G times R minus plus G H C. And notice that we want C to be alone. So then let's add or subtract this term here on the right. So we get C plus minus GHC is equal to GR. Then we can pull the C out, and then we get 1 plus or minus GH is equal to G times R. And then finally, when we divide both sides, we get G over 1 plus or minus GH multiplied by R. And that's how you get the feedback form. Any questions? And that's why it's plus or minus and not minus plus. Oh, I guess I was supposed to do the proof on that on this page. Oh. Let me move it to this page. Okay. Additional reduction methods here. So these are just some tricks that you can do. So then in red, I'm going to show you my method. So let's call the signal here the input x1. Then this output is going to be G times x1, and this output is going to be G. It's just going to be x1 because it's a pickoff point. And if you look here, if you look right here, x1, it's going to be multiplied by G, and we get G times x1. And then we get G times x1 multiplied by 1 over G. Then we just get x1 here. So these two are equivalent. So basically, if you move this block back, but the block doesn't exist here, you got to divide that signal by that block. So that's like pushing a block behind a pickoff point. Likewise, if you push a block past a summing junction, then you have to, then you have to do something similar. Oh, for this one? Yeah, I can explain that again. So if we were to take this G and we push it back here, we still want this output to be G times x1. So x1 is our signal. But this system now is going to get, if we check here, this is G times x1 here. And we need to get rid of that G. So we have to divide it by G to get x1. So these two are the same. That's how you can check if your block diagram reduction is working when you move stuff around to make sure that they're still equivalent. Does that answer your question?
Yes, thank you.
Okay. Now, for the second one, it's something that's similar. I'm missing an arrow here. Let's call this x1 again. If we look at that output here, this output, and let's call this x2. This output is going to be G, it's going to be plus or minus G times x1 plus or minus x2. Put that right above there. So let's still call this x2 here, and this is still x1 here. If we check this point, this is going to be x2 over G. So then if we check right here, we get plus or minus x1 plus or minus x2 over G. And then when we multiply this signal by G, then we get gx1 or plus or minus gx1 plus or minus x2. So these are both the same systems. Yeah.
Plus minus. Is it going to be clear whether or not it's like negative or positive feedback? Like, are we just gonna?
Yeah, I'll tell you if it's negative feedback. If I'm ever missing a sign, please ask me. But if I don't clarify, assume negative feedback. The reason why we want negative feedback is because we want to because our input is usually what we want and the output is what we have. So then we take the difference and that's the error. in cases where if it's positive, that's called positive feedback, and you're just adding on to that error. But positive feedback systems do exist. One example is, have you ever panicked before and it gets worse? And it gets worse and worse. That's a positive feedback system. Herding animals, positive feedback system. When one animal freaks out, the rest of the animals around that area, they also freak out. Then all of them freak out. Positive feedback. So they do exist, but usually for control systems, we want negative feedback. Yeah. So usually I just write this here just for thoroughness, but I will specify if it's plus or minus. And then this one might seem a little bit weird, but you can just break off different summing junctions. If we look here, P of S is just going to be equal to R plus R minus X minus Y. And we look here at this point, we get R minus X. And then we look here, we get R minus X minus Y. Same system. You can just deconstruct it like that. One other thing to note, and maybe I should update this for future slides. This signal here is also equal to that. You could just put a 1 there. The reason why you can do that is because then I can say, I can do this. I could put a -1. And then I can put a minus sign right here. Same signal. Just a lot of different ways of manipulating this. Or I could also do this as well. I can overcomplicate a signal. It's equal to maybe make this a little longer. I could do that. So I can add a signal, then add the same signal, then subtract it. And these are all the same. Now, there are reasons why we might do this, but it's not until I think chapter 6 or chapter 7 on steady state error, but just a little trick. There's like, if you can make block diagrams as simple or complicated as you can or want. So let's go over an example. Start with, this is a exam problem I gave in 2022. Wasn't a very popular one. 2022 midterm problem. And I'll show you both methods. I'll show you the way the textbook wants you to do it, and then I'll show you the signals method, where this is our block diagram. And so we have our input. So we have a summing junction here going into a first block G1. We got a second summing junction. We have G2 going into a third summing junction. Oh, a little heart. And we have our output. And we have this signal here that is feeding forward into the summing junction. That's going to be a plus sign. Oh, that's going to be a plus sign there. And then it feeds into both summing junctions. This is going to be minus. That's going to be a plus. And then we have this feedback. Positive. Sorry, it's going to be a plus sign. Try to make this look a little better. Okay. So I'm gonna have two methods. So I'm gonna split this page in half. I'll show you the textbook method. Show you that first. Then I'll show you the signals method. I only started teaching this method last year. I didn't teach it the first 2 years I taught it. And I think the signals method is a lot more intuitive. But I'll have you do both. Some people still chose the textbook method, which is fine. It's a personal preference. Straight line. There you go. Okay, so first thing, and there's more than one way of solving this. My solution isn't the only solution. You can reduce it. There's different ways of different approaches. But the first thing I did was I wanted to get rid of this signal here because I like the feedback here. Applying the feedback rule is pretty simple. So what I want to do for my first step is I want to take this signal and I want to push it past. Or yeah, push it. I want to push it past G1. So I have my input. Have that. And basically what I want to do is I want to have the signal come out from here instead. And here, I don't have, if I look at the signal, I don't have G1. But now that G1 is in the way, I have to divide it by G1. I think I'm going to run out of space. But I still have this feed forward signal as well. And this feed forward signal also does not have G1 in it. But now that G1 is in it, in this signal, I also have to divide it by 1 over G1. So there's a reason why I'm drawing it like this. Oh, and then there's the feedback now. So there's two things I can do now. One is you can see here, these are now parallel. So I can just add these two signals together. And so these are parallel. Then with a different color, this here is negative feedback. So let's apply negative feedback. well, it's not a plus sign anymore. It's just signal going straight into it. So negative feedback is going to be G divided by 1 plus GH. And here in this case, H is equal to 1. We get this parallel signal, which is going to be 1 plus 1 over G1. And this is going into G2. And then we still have this other signal. Like that. Now, this can be further simplified. We now have, oh, I'm missing a 1 over G1 here. Apologies. We now have another parallel signal. So this is also parallel. And we get this. We get G2 times 1 plus 1 over G1, because these two blocks are in series, plus 1 over G1, or sorry, it's going to be minus because of the minus sign, and then our output C. So then for our final block, we just multiply these two together because they're in series. We get G over 1 plus G multiplied by G2 times 1 plus 1 over G1 minus 1 over G1. If you want to simplify it, it's just going to be, C is going to be G2 plus G1 times G2 minus 1 divided by 1 minus G1 multiplied by R. Yeah. Yeah, sorry, it's G1. Thanks for pointing that out. All right. Now I'm going to show you the signals method, which I think is going to be a lot more intuitive. Let me call this X2. So this is going to be X1, and then, yeah. So basically for the signals method, I like to define my signal after summing junction. So if we look at X1 first, X1 is going to be equal to R plus, if we look at this line here, that's going to be G1 multiplied by itself. So then if we work this out, we can find that X1 is equal to R divided by 1 minus G1. All right. Now, if we look at X2, X2 is going to be equal to, so if this here is X1, then that means this is also X1 because they share the same pickoff point. So then X2 is going to be equal to X1 plus G times X1. G1 times X1. And then finally, we look at the output because we're trying to get the output. The only variables we should have are G, C, and R. The output's going to be negative x1 plus G2 x2. So we have three equations and two unknowns. And we can start subbing in x1 into all of these. So let's first solve for x2. X2 is going to be equal to R over 1 minus G1 plus G1 R over 1 minus G1. That's going to be equal to 1 plus G1 times R divided by 1 minus G1. Then now that we have x2 and x1, we can sub it into C. So C is going to be equal to minus R over 1 minus G1 plus G2 times 1 plus G1 divided by 1 minus G1 multiplied by R. So then our output is going to be equal to G2 plus G1 times G2 minus 1 divided by 1 minus G1 multiplied by R. That's our final answer. And they're both the same. Any questions? So you don't have to do that block diagram where you move stuff around and then you lose track of what you moved, or if things look very complicated, I usually just resort to using the signals method of checking my work. Or if you want, you just use the signals method of solving it. That's completely fine by me. It should be I want you to have the best tools available for you. So either method is fine by me. If you ever see this on the exam, either one works. Oh no. All right. Okay, so actually that I have another example, but I think I'll just post it online. The question is why does projector keeps disappearing? We just have to do one of the two methods on the exam. Yeah, that's fine by me. So whichever method you prefer. When I taught this last year, I think over 90% of the class chose the signals method over the textbook method, and the grade that year for the block diagram problem was much higher. I find it easier, but if you want to do the textbook method, that's fine by me too. Some people are more visual based, and that's fine. I'll post the second. I'm going to fill this in and I'll upload these notes today. I'm not going to go over the example, but I'll write down every step so you can go over more on the block diagram. I just want to wrap up this chapter so we can start on lecture 2 on Monday. So some takeaways from this section: controllers are only useful when you get your desired response. Block diagrams shows the subsystems in a system, so we can take a single block and break it out into multiple subsystems, and then we can combine these blocks into equivalent blocks for analysis. So if we put this really complicated block back into feedback form, it makes it really easy to apply equations or apply analysis on it, especially when we're going into PID design or Bode plots, or we're looking at stability using different methods where feedback form is useful. So that's about it. Next class, we're going to go over just some math review and talk about Laplace transform, which is chapter 2. All right, thank you.